Okay, chat AI, here's my prompt. Create a video script answering the question, can AI replace neutrino physicists, for my Fermilab YouTube series, Even Bananas, with my new AI co-host, Nina.
My name is Nina, your AI-generated presenter, and I am replacing Kirsty Duffy as host on Even Bananas.
Whoa, don't worry, I'm still here. That got a little awkward. I'll have to figure out a better prompt for the AI overlords. Hopefully, we'll get Nina sorted out before the end of the episode. If you've had the opportunity to use one of these AI services lately, you know they're all the rage right now. You can engage these various AIs to answer burning questions, create songs, artwork, and video, or even to get some slightly incorrect facts about neutrinos. More on that later. But did you know particle physicists were some of the first adopters of artificial intelligence? Today, I've invited Hewes, a postdoctoral researcher at the University of Cincinnati who works on Nova and Dune, to discuss how AI is used in neutrino research.
Hi, Kirsty. I prefer to talk about it as machine learning rather than artificial intelligence because there's nothing really intelligent about it. It's just a bunch of vector algebra, and now we have computers that can do huge amounts of vector algebra really fast.
Yeah, it's a good point. AI or machine learning is really not as mystical as we often think.
Machine learning techniques have seen increasingly widespread use in neutrino physics for a variety of different tasks. One of the biggest is event classification, like deciding whether an interaction in your detector is an interesting neutrino interaction or just a cosmic ray. One of the simplest tools for this kind of task is something called a boosted decision tree, or BDT. These are algorithms that can look at a number of variables and return a score for how likely it is that a particular object is signal or background.
For example, imagine I'm using a classification algorithm to work out whether this picture is a cat or not. I give it variables, which are just bits of information, like there are two pointy ears or there is fur. And we train the algorithm by giving it lots of examples. And for each example, we tell it whether it's a cat or not. The algorithm then learns what bits of information signify cats and what things are not what it's looking for.
The hope is that the algorithm can find connections that we didn't, and therefore be better at identifying events than just asking simple yes/no questions about each of these pieces of information.
Another way machine learning is used in neutrino physics is to do something called reconstruction. That basically means looking at the raw data from our particle detectors and converting it into information, such as there was a particle here, it had this much energy, or even it was probably a muon and not a neutrino. Reconstruction is how we produce our variables from the raw data.
Many experiments, including Nova, have used convolutional neural networks, or CNNs, for reconstruction. We have found them to be much more efficient in some cases than traditional reconstruction algorithms.
CNNs are machine vision algorithms, so they run on pictures. For example, we might show one this picture and ask, is there fur? Or we could ask something more complicated, like, is the cat alive or dead?
For certain detectors, like the Nova detectors, the data that's read out is natively structured like an image, so using CNN technology is a natural fit. But for other detectors, the data isn't so naturally image-shaped. So in order to use CNNs, you end up having to restructure the data to make it image-shaped, which isn't really ideal. That's why my current machine learning research focuses on graph neural networks, or GNNs. These are deep learning networks like CNNs, but they're more flexible in terms of the input format and can be applied more naturally to a much broader range of detector technologies. In fact, the graph network I'm developing at the moment uses a very similar approach to some of the AI chatbots you might have used to, say, write a video script.
The ideas for CNNs and GNNs have been around for a long time, but they've only started to be feasible recently with modern GPUs and supercomputers that are powerful enough to train them.
That's right. Many of the recent advances in machine learning are really mostly down to advances in computing. A lot of my work uses the Wilson cluster at Fermilab, which is a high-performance computing facility using a large number of GPU nodes.
So V, this has all been really interesting, but do you think that AI, machine learning will ever replace us neutrino physicists?
No. Machine learning algorithms are powerful tools, and they help us with our work, but they are still tools, and they require oversight by experts who know how to use them responsibly. It's really important to think carefully about what information you give to these algorithms, or you can accidentally bias the results. You need to consider both what information you give it and what's in the training dataset to make sure it's learning the right things. We often describe this as garbage in, garbage out.
Yes, I found that out with my prompt at the beginning of the show.
Even at their best, machine learning algorithms are not originating interesting questions, developing theories, or testing them experimentally on their own. So they need us more than we need them.
Phew, well that's a relief. Thanks, V. To take us home, I'd like to invite back my AI co-host, Nina.
Hi again, it's Nina, your AI presenter. Thank you for watching today's video. If you enjoyed this video, share it with your friends and let them know about it. And don't forget to like and subscribe for more neutrino fun.
Okay, I think our jobs are safe for now. Author Neil Gaiman recently said that AI doesn't give you information, it gives you information-shaped sentences. That's pretty accurate. AI chatbots have confidently told me many things about neutrinos that are not true facts. Here's my personal favourite. Neutrinos cannot be created or destroyed. This is something we all learn at school applies to energy, not so much for neutrinos. It goes on. For example, when a neutron decays into a proton, an electron, and an electron antineutrino, the total number of neutrinos is conserved, even though a new neutrino is produced. I mean, what?